Let's consider something seemingly very simple, and that is two masses on a pulley. They're not necessarily at the same height. They're not necessarily the same mass. So there's M1 and M2, and we're going to ask what's going to happen to them, especially if the mass is different. Well, of course, if the mass is different and this pulley is frictionless and held up by something else, then they're going to accelerate. Let's take the case when M2 is bigger than M1, which is as I've drawn it. In that situation, M1 is going to accelerate up and M2 is going to accelerate down. I'm going to draw two separate free body diagrams, one for M1 and one for M2. And we're going to try and resolve what that acceleration is. So M1 has two forces acting on it. It's got its weight, which obviously points down, and it's got the tension force coming from the string. M2 also has the same tension force, but it's got a different weight force. So the thing that's common in these different free body diagrams is the tension force. It both is T in both cases, and it's acting up. And in our actual kinematic situation, the thing that's common is the magnitude of the acceleration, although the direction is equal and opposite. And hopefully you can see that these will be accelerated at the same rate, just in different directions. So let's try and put this free body diagram into equations using Newton's second law. For the first mass, we're going to get m times a. Let's take the vertical component of the acceleration to be positive a, and that's equal to t minus w1. So we're now looking at the vertical component so that a is positive, t is positive, and w1 is the magnitude of the weight force, and it's gives us a negative sign because it's downwards going weight force. Newton's second law for the second mass, well, again, we consider the vertical component of the acceleration. Now it's negative a. We times that by m to get the net force in the vertical direction, which is t minus w2. So we've got two equations, and we've got two unknowns. We don't know t, and we don't know a. If we wanted to find a, the simplest thing to do here is just eliminate t. We can do that by writing, and I forgot my 1s and 2s on the masses, of course. Now our job is to isolate a. We do that by bringing the masses times a across one side of the equation and all the weights on the other side of the equation. I'm going to highlight this equation because it looks fairly interesting. In fact, it kind of looks like some magical version of Newton's second law. But for the time being, I'm just going to push ahead and actually solve for what a is algebraically. So the magnitude of this acceleration is the difference in the weights divided by the sum of the masses. And there's actually a more elegant way to express that if we took the ratio of a divided by g. So here we can see that the ratio of the acceleration to the gravitational field strength is actually just a difference in masses divided by the sum of the masses. So now we have this dimensionless quantity on each side of the equation. That's pretty cool, and we can already think of some consequences of that. So imagine if these masses were really, really big and they only differed by a small amount. Let's take M1 be equal to some big mass m, and M2 equal to the same big mass m plus a little m here. Now you'll see that this acceleration, or the acceleration over g, is just equal to the difference in masses, which is the little m, divided by 2 lots of the big M plus little m. And if we're in this situation where big M is big and little m is little, then we can say that's approximately equal to m over 2m. So what does this mean? It means that if I'm standing on some 1-ton weight, and that weight is connected to a pulley, and on the other side of that pulley there's another 1-ton weight, I'm not going to fall at 9.8 meters per second squared. I'm going to fall at a small fraction of that. In fact, I'll probably fall at less than 10% of g. So this effect of having large masses that only differ by a small amount is to kind of give you a decreased inertia or a decreased gravitational acceleration. That's pretty cool. I'll still accelerate, but just not as fast. Let's now come back to this expression here and ask, could we have figured this out using intuition? So is there something here inherent that gives us some physical reason to think that we could have just eyeballed this equation? Or indeed, can we hand wave some physics to explain the equation? And one of the reasons or motivations for doing that is to think that this is Newton's second law in some form. One concise way of asking that question is to say, there's a mass times an acceleration, and it's equal to something which has units of newtons, a force. So is that Newton's second law for something? And if so, what is it Newton's second law for? Well, the fact that there's a mass which is the sum of the two masses might hint that it's the Newton's second law for the entire system, the composite system of M1 and M2. But then we have to reconcile what is A, and also what is this difference in weights doing on the right-hand side. It turns out that this is actually not correct. It's not a correct way to think about Newton's second law, because A does not describe the acceleration of that composite system. That composite system is accelerating at a very different rate to A, and indeed A only describes the acceleration of each of the components of that system. So if we were to think of the whole system combined, we would actually have to use the center of mass displacement of these two bodies and define a new set of coordinates for that. And if we did that, we'd find that the true acceleration of the combined system, described by its center of mass, it actually looks like the acceleration we found for each of the masses, but it even depends more strongly on this quotient of the mass difference divided by the mass sum. And here's where we have this conundrum. This is not an equation describing Newton's second law for anything. It's not an equation describing Newton's second law for either of the masses, nor is it an equation describing Newton's second law for the entire system of M1 and M2. So we're actually no smarter in terms of a hand wave or an intuition than we were when we started, but we did learn some physics about the combined system's inertia and this counterintuitive result that if you stand on a 1-ton mass, you don't always accelerate down at 9.8 meters per second squared.